I'm Alex from Uber, from Machine Learning Platform. Our job is to make everybody successful with deep learning and be able to train models in hours instead of months. So why people talk about deep learning these days? This is a famous slide from Andrew and G, and basically what it shows is as you continue to grow size of data that your organization have, traditional machine learning algorithms start to lose, your performance start to kind of become constant. And so as you naturally grow more data, you don't get further benefits. And this is where deep learning is helpful in the sense that it can continue growing your accuracy or metrics that you care about, which can turn into business value for you. There is few, right now deep learning is quite, it's state of the art for many domains. It's state of the art for vision, for machine translation, for sound processing. And so it's very natural for us as a company to be able to leverage some of the new research that happens in the community. That's why deep learning is great. And we use it for a lot of things. So we use it for self-driving cars, obviously, because there's a lot of image processing, video processing, LiDAR processing, control systems. We use it for trip forecasting, where we want to know, okay, it's going to be next new year, how many people will try to drive Uber or ride Uber, what's going to be distribution across the city, how we can predict that. Fraud detection, we want to make sure that everybody is doing are honest on the platform and not trying to cheat, and so that way we can maximize earnings for drivers and minimize price for riders. And there is many more use cases that I cannot cover here. So how does it work? It's pretty simple. The reason deep learning is called deep learning is because when you do your data prediction, you essentially pass your data through a series of consecutive transformations. And more transformations you do, the deeper it is. Initially, what was called artificial neural networks before would typically use one or two of those transformations. And now it became deep learning because now you do hundreds or thousands of those transformations. And so when you do training, you typically what you do is you pass, if you do supervised training, you pass data and label to your model. So label is your expected output for a given data. And data goes to the whole model. You get prediction, which could be right or could be wrong. In case if it's wrong, you see that you made a mistake and you want to correct your weights in a way that your model will become more close to model that will predict this correct label for this data in future. And so what you do is you compute these gradients going backward in the model. So you basically first do this forward pass for the model, then you do backward pass. And after you did both of those, then you can start next iteration of your training. So as I mentioned, you get most benefits from deep learning when you have more data. And so when you have a lot of data, that makes things slow because your machines can only ingest so much data at a second. GPUs can only train so many images per second. And we need to have some solution to still be able to train those big models on a lot of data in reasonable time. So engineers can have a mentality of quick iteration. Because for engineers, it's pretty easy to get in a state that, OK, I'm going to kick off this training. It's going to take a week. So I need to do something else, maybe twiddle my thumbs or think of some theoretical things. Or I'm going to spin up 10,000 hyperparameter searches, trying to search this space and see what's going to happen. Frequently what happens is they did spin up 10,000 hyperparameter searches, but then all of them converge to nothing because there was some fundamental issue that they found after that week. And so being able to train models quicker, maybe using same amount of resources, but quicker every time, allows you to get to the right model with way less iterations. And so if you think about these big models and big data, you could think of either distributing data across machines or building a model so big that it doesn't fit in a single machine. What we see right now is that modern hardware has good capacity in terms of memory. If you go to AWS, you have 128 gig of GPU memory, same in GCP. If you buy fancy DGX2 machine, you get 500 gig of GPU memory, which fits almost all the models that you can dream of, unless you're Google. And so because of that, biggest recipe is to basically use data parallel training. And so the way data parallel training works is you have these copies of the model that you pass the data through. Model is the same, data is different. You compute the gradients independently, then you average gradients, and then you do next iteration. And so there are a lot of ways how to do this data parallel training. All the frameworks have slightly different flavor of it. UX is good in some frameworks, it's worse in other frameworks. And we see that a lot of researchers actually flip between frameworks quite a bit. Because let's say Google or Facebook or other company publish new paper, and you want to try this paper, this approach on your data. So what you do is you take their code from GitHub, you try to apply it to their data. Your data is big, so you need to do distributed training. You need to figure out, okay, how do I distribute this framework? How do I distribute that framework on my system? And so with our platform team, we had kind of two goals, how we can enable people to be successful. So one goal is for infrastructure people, like me. We need to choose servers. We need to choose network hardware. We need to choose container environment. We need to choose default containers for people to use if they don't want to build their own. We want to tune distributed training performance of the whole system on like system level. And we want ML engineers to not worry about any of that. ML engineers don't need to be systems people. They don't know how distributed training works. They just need to build great models using frameworks that they love, which may change on a daily basis. And so that's why we built Horovod. So Horovod is a library for distributing deep learning frameworks. It works with TensorFlow, Keras, TF Keras, PyTorch, and we have ongoing contribution for other frameworks as well. And it's really easy to add another framework if you have something that you really love and it's not here. It installs on top of frameworks by a simple pip install. So you install latest version of TensorFlow or whatever version you like, whatever version of PyTorch, and then you install Horovod. You don't need to have special version or anything special with the framework. It uses advanced algorithms that I'm going to cover a little bit later in the presentation, and can leverage wide range of networking technologies that may make it perform way better than it would otherwise. And it separates concerns between different actors. So infrastructure people can set up environment needed for it to work great. And machine learning engineers can just train the models, make super simple modification, and go from training a single GPU to training on 1,000 GPUs. So how does it work? Primary driving factor in Horovod is algorithm called ring all-reduce that I'm going to cover pretty quickly. Basically, the idea here is this example. We have 3 workers. Each of them have 6 numbers. And the goal is in the end to have average, or in this example, sum, in every position across all 3 workers. So what ring all-reduce does is it partitions those buffers on each worker into number of segments that is equal to number of workers. And there is 2 phases of algorithm. In the first phase, you send data from one worker and receive data from one worker, and also add numbers. And in the end of this first phase, in one of the positions in the buffer, you will have the right answer for that column. And the second portion of the algorithm does distribute that value. So what happens is it follows the amount of steps that you do in this algorithm is proportional to the number of workers. But the amount of data that you send is not proportional to the number of workers. It's almost constant on average. It's constant to the total number of data you have per worker. The reason is we actually send very small buffers. And so if your initial buffer is very large, you can see that on every iteration we actually send pretty small amount of data. And total summation of data will be constant. It will be just function of this size rather than million of workers that you may have. This holds if your buffer is reasonably big, because if your buffer is too small and you have million workers, it may be hard to divide, let's say, 1 megabyte into a million pieces, and send 1 byte is not going to be more effective than send 1 kilobyte because it's still the same packet. But for large buffers, like gigabytes buffers, it holds pretty well. There is paper by these fine people who promoted this algorithm, and they claim that it's bandwidth optimal for this reason. So Horovod stack, as I mentioned, it installs on top of TensorFlow. It uses MPI for worker coordination. The reason we need worker coordination is because TensorFlow does perform operation in a non-deterministic way. So when I mentioned here, we do this layer computation. When we compute these gradients here, It's actually one worker could compute this gradient first, then this gradient, the other worker could do it the other way. So we use coordination to make sure that we resolve any conflicts between these workers. And we use Nickel, which is NVIDIA optimized all-reduce and other collective communication library for actual very fast all-reduce. So how do we use it? It's hopefully quite simple. So first you initialize the library. You just import it and do hvdid. You pin GPU to be used. So TensorFlow, if you just run it, by default likes to use all the GPUs it can find in the system. We typically run Horovod in a way that you run single GPU per process. And so because of that, we need to specify which GPU you should use for every process. So in this example, what we see is that when we do MPI run on these two hosts, each host has two GPUs, it shows kind of two concepts that we have in MPI. One is called rank, and another is local rank. So rank is universal idea of your process in the whole world of this run. Whereas local rank is rank within a server. And so it's very natural to use GPU that is identified by local rank. And we provide primitive to get that local rank and plumb it to TensorFlow. Another thing that you need to do is you need to use Horovod distributed optimizer on top of your optimizer that you like to use. It can be anything. It can be momentum, SGD, Atom, pretty much anything. And you need to adjust learning rate. So adjusting learning rate is one of the interesting aspects, and it's open research space. There is quick and dirty rules, like Facebook popularized a linear scaling rule. So basically what you do is you multiply your single GPU learning rate by the number of GPUs that you have. If you have a lot of GPUs, let's say in their paper they used 256 GPUs, you also need to do a little bit of warm-up. So in the first few iterations, you don't start with very large learning rate, you start with small. And then over first couple of epochs, you scale that learning rate up. In Keras, we provide callback for you to just include in your code that will automatically do this warm-up. But it's not hard to do in pretty much any framework. And in our examples, you can find that callback and adapt it to your needs. Other important part is synchronized initial state. So when you launch your training, let's say you didn't start from checkpoint, so you're starting from scratch, your workers will all start with some random set of weights. And so if you average gradients across those weights, they, as in this example, may point not where you want them to point. So they'll all point to the center individually, but not collectively. And so to avoid that, what we do is we pick one of the workers as golden state, and we replicate that state to everyone using broadcast. Typically, we broadcast from the first worker. And so there is two examples how to do it. In TensorFlow, there is a lot of APIs that you can use. Our goal is to work with pretty much any API that you like to use. And so here we have two examples, one using monitor training session, another using just normal TF session, how to do this broadcast. Another piece that is important, it's simple, but sometimes overlooked, is how do you do checkpointing? So because all your processes run exactly the same code, they all, by default, would write checkpoint to the disk. Sometimes you have multiple GPUs on your system, then you would write multiple checkpoints, typically in the same file. That will not end well. And so recommendation is to just write checkpoint on the first rank, because all of them will have exactly the same model state. So it doesn't make sense to write everywhere. You don't really need to solve this problem. You just save it in on one rank, and you're good. And so if we take all this together, this is full example how you would do your training of your model. And the model is hidden in these three dots. So we're not talking about how to define models. We're just talking about how to scale them, which is pretty concise. And so we talked about TensorFlow, but there is more. So this is how you do TensorFlow, but we have Keras and PyTorch. And one of our goals, as I said before, was to make it really easy for users to switch frameworks. And so here's a full example how you do this same stuff in Keras. And as you can see, it's pretty much the same. You still pin GPU, you still change your learning rate, you still wrap the optimizer, and you still do the callback to do the broadcasting. So names are a little bit different, but concepts are all exactly the same. Same for Estimator API. Estimator API is one of the newer APIs that TensorFlow released. Also, so they use this estimator. You still do pretty much same set of steps, and the APIs look pretty much exactly the same. And as one of the more recent additions, we also added PyTorch support, because a lot of our data scientists like to switch back and forth. And even in PyTorch, we managed to preserve pretty much same APIs. You still specify GPU, you specify optimizer wrapping, you still broadcast parameters. The parameters here are also a little bit different, but you know the steps that you need to do, and it's just a matter of kind of looking them up in a syntax how to do it. So how do you run Horovod? Typically we use MPI, and so if you just use OpenMPI, one of the latest OpenMPIs, you need to do, let's say, execute this command, what it will do is will run 4 processes on a current machine. So let's say you have 4 GPUs, then it will run 4 processes. If you have 4 machines with 4 GPUs, you can run this command. So there is some brittle code that you always need to put, and pro tip is for your environment, you just create this boilerplate wrapper script that will hide all this from user. So user will not run actually this, he will run mpi run.sh and just his command. And what it does, you as an infrastructure engineer can define what kind of network interfaces you use in your environment, what kind of other flags you may need to set to get best performance, but your machine learning engineers don't have to deal with any of that. And so one of the recent additions that is currently in pull request, but you are very welcome to try it out today, is Horovod on Spark. So on Spark, what you can do is you don't need to do MPI run. Instead, you can define your training here as a function. And I completely avoided pretty much any code of the actual model, but imagine you have put the examples that I've shown before in this function. And so then what you can do is you can start your training just using this Horovod Spark run. And what it will do, it will start your training on your Spark cluster. You may do it on CPUs if your model is small enough, or you may set up your Spark cluster on GPU machines and then just use Spark for both data processing and data training. And how would you do training loops? So one of the ideas here is that you can actually use Spark for validation, native Spark RDDs to execute validation, and you can use this Horovod training for actually running training runs. So this way you can hide complexity of launching MPI run. It allows user to leverage existing Spark infrastructure that many people have in their company. You can do data preparation and training in the same environment. So oftentimes you do a lot of data extraction, data massage before you actually do training. And in these environments, this helps quite a bit. And so one of the pro tips is for reading data inside this training function, you can actually use Petastorm. And so what you use is you save your RDD into Parquet format, and then use Petastorm, which is a different library that we recently open sourced, that allows you to do randomized reading from Parquet files. So typically doing randomized reading from something in Spark is quite a bit hard, and Petastorm is optimized exactly for this scenario and integrates quite well. So hopefully all this talk before convinced you that it's reasonably easy to use. And so now let's talk about performance. What we observed in our environment is that we get really good scaling with Horovod. So we scaled to 512 GPUs, and we got around 90% scale and efficiency for common models like Inception and ResNet. We did get around, I would say, 70% with VGG, and VGG is really hard to scale. The reason is VGG has a lot of weights, and it's very short. And it's very easy to compute back and forth, but amount of data that you need to send is quite a bit big. It's actually, I think, bigger than ResNet. And so because of that, many frameworks have way worse scale and efficiency, but we still see that some of the models, they still use fully connected weights, which are root cause of these big layers. So it works pretty well in these scenarios as well. So how do you get most of the Horovod? So let's say you start running, you see some performance, you're curious, can you improve this performance? So there is some tuning knobs that you can try to adjust and see if it helps you. One of the recent additions that we did with help of NVIDIA and Amazon is hierarchical reduce. This works on really large environments, but also works in some of the smaller environments under certain situations. So what it does, instead of doing one single ring reduce, it does hierarchical reduce that I will describe in a little more detail in just a second. One other thing that we have is Tensor Fusion. Tensor Fusion was there right from the beginning. And what it does is it actually batches small or reduced operations. So if you think about ResNet, let's say ResNet 155, it has 155 layers, and it has around 500 tensors. A lot of those tensors are really super small. And so what you want is, you don't want to run all reduce and do all the coordination for every little tensor. So what we do is we batch those smaller reduces until we get, let's say, 64 megabytes, which is this default fusion threshold that we see. And we do this analysis every 5 milliseconds, which is the cycle time. So you can actually adjust both of those parameters and see what works better for your model and your environment. And finally, we have added FP16 all reduce. So what it does is, instead of doing all reduce using full precision weights, like FP32 weights, what it does is, you can still train your model in FP32, but before doing all reduce, it will cast your weights down to FP16, do all reduce, and then cast it back. So what we found is two things. First, when you do FP16 training, it's actually quite challenging, because some of the layers, they tend to have very different weight distribution and activation distribution, and there is techniques that you need to apply to actually make it work. There is some things called mixed precision training that, if you're interested, NVIDIA has written up quite a bit of information about it. What we found about all reduce, though, is that it actually is way less sensitive to this reduced precision. And so when we did this very naive experiments without any rescaling, just running ResNet training, we see that we have no changes in accuracy when we do this FP16 training. But what we saw, if we run it in less than ideal environment, we see up to 15% or 70% speed up. So it's something to try. It's not unlike these previous things, it's not guaranteed that it will not change your model outcome. So it's something that you need to opt in, but it can give you better performance. And so hierarchical reduce is quite interesting, so I wanted to spend a little bit of time on it. Okay, so basically it's similar situation to before. Now we have 4 processes and 2 machines, and each of them has 4 numbers. So what we do is, it's 3-stage algorithm. In the first stage, we do so-called reduce scatter, and we use it using nickel. So for reduce scatter, on the first 2 digits, we all reduce on the first half of the tensor, and it ends up on the first rank. Then we all reduce second half, it ends up on the second machine. Same for the other server. So after that, we get ground truth for within a host, but it's spread around. Then what we do is we do parallel all reduce for rings that are formed around local GPU ID. So for all the first GPUs will have one ring against each other, all the second GPUs will have a ring for each other, and so on and so forth. And then we do local altogether in the end. So this algorithm allowed us to actually scale quite well on the large systems. We do have users from national laboratories like Oak Ridge, where they have 27,000 GPUs. And algorithms like that help them scale way better than just single ring all reduce. So I also want to talk a little bit about Horovod Future and how we're looking about making it easier to use. So this chart shows you how changes in these parameters that I told you affect outcomes. So blue line here is nickel, and the green line here is hierarchical reduce. And so you see that typically they behave differently. In some cases, one wins, in other cases, other wins. And it also depends on the cycle time, it depends on the fusion buffer, which is on top. So it's kind of hard and time consuming for you to find this best value. And so what we're doing right now is we're adding Bayesian optimization, auto-tuning, which will try various combinations during first few dozens of iterations. And after that, you will not have to worry about finding the right combination. We're evaluating whether this can find this right combination for you, and so far we see that in most instances it does. And other improvement is further gradient compression. So we see in FP16, we're looking into using 4-bit. We're looking into using gradient compression, which is stochastic gradient compression, which allows you to save up to 10,000 times or 1,000 times on bandwidth. So for example, sometimes people come and ask, hey, I have this cluster of GPUs, I have 1 gigabit network between them. Right now we say, sorry, you cannot do anything with this. But with things like gradient compression, we could. and right now it's active area of research. So my last slide is what did we get with it and how do we use it. So in Uber, Horovod is the only way to do distributed deep learning. We train convolutional networks, LSTMs, and other models. We train them in hours instead of weeks that it used to take before. Horovod is used by other companies, so it's used by Amazon, NVIDIA, Alibaba, and various research institutions quite a bit. It's included in various deep learning distributions, so all the cloud providers, AWS, GCP, Azure, they have Horovod in their default VMs. NVIDIA GPU Cloud. IBM has it in their Fabric for Deep Learning, which is another open source project that they released. They have it in their Watson Studio and in Databricks runtime. So it's quite a bit used. We'll be really happy if you guys find it useful for your cases. Please let us know. Please let us know if it works for you or if it doesn't work for you, and if it doesn't, how we can make it better. And then I'll say thank you.
Thanks very much, Alex. So I'm sure there are some questions.
So when you have like several models on different GPUs, so you update the gradients, you average them within the GPU. But how do you update the model? Do you like average all the gradients afterwards and then update the model, or you do like kind of micro mini batches?
So if
model from one gradients, then from another, third, and fourth, and then you like update everywhere and distribute everywhere.
Right, so the question was, we have all these models, and how do we update gradients against them? So what we do is, here we see 3 blue boxes. In reality, is let's say you have 1,000 GPUs, there will be 1,000 boxes. And whenever you do training, whenever you compute gradient, we start all reduce of like averaging of this gradient across all 1,000 models. So this ring is 1,000 GPU ring. Now at 1,000, it may already start to be more reasonable to use this hierarchical algorithm, but this one operation of averaging covers the whole universe. Sure?
So my question is regarding the data. So you did say that the data is broadcasted between all the worker nodes, right? So I'm trying to understand what happens in the cluster, or what is the mechanism in case one of the worker nodes goes down.
Got it. Everything crashes. MPI and nickel are not fault tolerant. They just crash. So what typically you do is you actually write checkpoints quite frequently. And when you crash, you restart from last checkpoint. Typically, when you think about these environments, you actually think more of HPC environment, where you have these like very expensive servers. If you look at list price of DGX1 or DGX2, they're quite expensive. So you have these expensive servers, which are not supposed to fail very frequently. And you also use way less of them than if you do it, let's say, Spark MapReduce job. So we don't see that much issues with failures in a single job. They happen sometimes, but they happen rare enough for you to be able to just restart from the last checkpoint and not spend too much money or time.